Good morning everyone. Most of you know evaporation, the process where we remove a liquid to leave a solid behind. But today, we're talking about recrystallization. While evaporation is about removal, recrystallization is about refinement. Recrystallization is a precision technique. We use it when we have a solid that is mostly pure but contains small amounts of unwanted impurities, and we need to separate that solid into a pure, crystalline state. The entire process hinges on one critical concept, the saturated solution. Think of a saturated solution as a chemical capacity limit. By definition, it is a solution that has dissolved every possible bit of solid it can hold at a specific temperature. In other words, the solvent is completely full. Every drop of liquid is already working as hard as it can just to keep the solid in a dissolved state. If you were to add even one more grain of solid to this mixture, it wouldn't dissolve, it would simply sink to the bottom. Understanding this limit is vital because, in recrystallization, we are going to manipulate this fullness to force our desired substance out of the liquid and into a pure solid form. There are two primary ways we prepare this. First, room temperature method, adding solid to a solvent at room temperature until it simply stops dissolving. Second, the hot method, adding just enough boiling or hot solvent to melt that solid into the liquid. Why does this matter? Because for recrystallization to work, the solution must be saturated only with the substance you want. We want our impurities to stay in the liquid, not join the crystal party. Once we have prepared our saturated solution, we begin the waiting game. This is the phase where the actual purification happens through either slow cooling or slow evaporation. As the environment changes, either the temperature drops or the volume of liquid decreases, the solvent loses its ability to hold all that dissolved solid. Because the solution was already at its limit, it becomes supersaturated, and the molecules of our desired substance begin to seek each other out. They start locking together in a highly organized, repeating geometric pattern. This is the birth of the crystal. This is the most brilliant part of the process, because the impurities are present in such small amounts, they simply don't fit into the rigid, perfect shape of the growing crystal lattice. They remain trapped in the surrounding liquid while the desired substance builds itself into a structure of high purity. We aren't just crashing a solid out of a liquid, we are allowing it to organize itself away from the waste. Once the cooling or evaporation is complete, you'll see the results of your patience, beautiful crystals sitting at the bottom of the beaker. But the job isn't done yet. We still need to physically isolate these pure solids from the mother liquor, the remaining liquid that now holds all the concentrated impurities. Depending on how your crystals grew, we use one of two methods for recovery. First, there is hand separation. This is rare but satisfying. If the process was very slow and steady, you might have grown a few large, distinct, chunky crystals. In this case, you can simply use tweezers to lift them out one by one. However, the far more common scenario is filtration. Usually, you'll have a mass of thousands of tiny crystals, a slurry. We pour this entire mixture through filter paper. The paper acts as a microscopic gatekeeper. It catches the pure solid crystals on top while allowing the dirty solvent, containing the dissolved impurities, to pass through into the flask below. Whether by hand or by filter, the goal is the same, to leave the impurities behind in the liquid and walk away with a pure, solid product. As we wrap up, you will often hear this process called fractional crystallization. Don't let the technical name intimidate you. The term fractional simply emphasizes the core goal. We are fractionating, or strategically picking out, one specific chemical fraction from a mixture of impurities. Think of it as a chemical filter that operates at the molecular level. By controlling the environment, we allow the desired substance to exit the solution as a solid, while the unwanted impurities remain trapped in the liquid phase. In summary, we dissolve the solid, create a saturated state, allow it to cool or evaporate, and finally, filter out the results. The outcome isn't just a recovered solid, it is a substance far purer, more organized, and more refined than what we started with. That is the power of recrystallization. That's it for recrystallization. If you found this helpful, let's keep the chemistry going. Saturate the like button. If you learned something new today, give us a thumbs up. Filter and share. Send this to a friend who needs help with their chem lab. Subscribe, join the channel so you never miss a lesson. Thanks for watching. Stay curious